So, pertaining to waves, we've now covered the ideas of reflection, the law of reflection. We've covered refraction, and we've discussed dispersion. Now, another idea is diffraction. So, diffraction, I say due to refraction. You're going to see it's very similar in that it's the bending of waves. It's the bending of waves around barriers. All right, or anti-barriers, namely a space through which the wave energy can travel. So we'll see what that looks like. And this is best illustrated with a ripple tank, which you may be seeing as we learn this or outside of that time. In any case, this is kind of be a summary if we do some tests with this. But if we don't do the test, we'll summarize it here anyways. So how does the amount of diffraction or bending depend on the wavelength, which means frequency also, for a constant slit size? So here's a slit. And these are barriers, and we have the wavefront. We have a wavefront coming toward it. Now, you would think probably that as this wavefront hits this is kind of what I mean by an anti-barrier in a sense. The wave can pass through this region and it's barricaded on the opposite sides versus having an object here that's just blocking a little part of it. So this part of the wave can get through, and you might expect it to just be a straight, square, unaltered wavefront coming through there. It's not the case. I'm considering this a long wavelength. In other words, this is long wavelength or low rate of periodic vibration to produce those waves, so low frequency. Well, it looks kind of like this. You'll see the wave fronts become bent. They'll bend a lot. So part of this is coming up here and going like that and moving out. So you see a lot of bending here, and it becomes more of a circular wavefront. Okay, and you can see the energy, the wave energy, is at very shallow angles out here, which means it really had to bend around to get that energy out there. So let's do a medium wavelength, something like this, and let's pass it through, and with the results we see look something like that. So we see considerable bending, but less than before. Notice we don't have any energy out here, so it didn't get bent as much. And then even a shorter wavelength or higher frequency looks like this, something like this. Notice that it's getting closer to just passing straight through without being bent, but it is being bent to a certain degree. So the conclusion from this summary is that the amount of diffraction or bending increases from here to here to here. So it increases with wavelength. Bigger wavelength, more diffraction. All right, so how does it depend on the slit width? So let's just use a constant wavelength this time and change the slit width. So our wavelength of choice is the distance between these crests, and we see a certain amount of bending based on this slit. Not very much in this case, all right? And now let's do a real small one. With a small slit, you notice a lot more bending. So that gives us the idea right there. We can make some conclusions from this. And I'm going to conclude, my conclusions are going to be based on this ratio. Because if the ratio lambda over d is small, it's kind of saying those are both doing the same thing. In other words, to make this ratio small, wavelength has to be small. That'd be like this. With small wavelength, there's not much bending. Or d is large. With d being large here, not much bending. So it's weak diffraction. Weak diffraction. And by the same token, if that ratio is large, then we're talking about a large wavelength or a small amount of slit width, and that results in strong diffraction, a lot of bending.